Hello, I'm Nawaz Ahmed. In this video, I am presenting a spreadsheet I have developed for design and drafting of RC beams. The sheet links with ETABS to import data from ETABS. Envelope is created within the sheet, the beams are designed and finally drawn in AutoCAD. Following are some of special features. The program looks for the point of curtailment. This will help in achieving some amount of economy. To show how this works, I will set the top right first layer of steel to 3 of 20, top midspan steel to 2 of 20, and top right second layer steel to 2 of 12. Now to curtail 3 of 20, the program will look for the point where 2 of 20, which is top midspan steel, is sufficient, and to this distance development length for curtailment is added and is displayed in terms of ratio. This is the ratio of curtailment distance to clear span. Similarly, to curtail second layer of steel, the program will look for the point where 3 of 20, which is first layer steel, is sufficient, and development is added and displayed in terms of ratio. The user can either go with these distances for drafting and for plotting graphs, or the user can set default distances for each layer of steel in design data sheet. To do this in design data sheet, I will set the optimize curtailment length option to no and set default values of curtailment for each layer of steel over here. These values will be used to update graphs and to draw beams in AutoCAD. Further, if the user wants to override the lengths at specific locations, he can do it by typing / followed by the distance ratio. For example, if I must extend the top left second layer steel up to 0.5 times of clear span, I will type / followed by 0.5 after 3 of 12. The weight of steel is displayed over here. The user can take advantage of this for economical design. Coming to graphs, there are 5 graphs. First graph from top shows bending moment, second shows shear force, fourth graph shows area of steel required at top and bottom, third and fifth graph are surface graphs that show area of steel required and provided with and without development length. Fifth graph alone is very much helpful for design. In this graph, the green surface represents area of steel provided and the brown surface represents steel required. Development lengths are not included in this graph. The user gets a very quick feel about steel provided if it is too high or less, or if steel is provided over unnecessary range. The third graph is similar to fifth graph except that it includes development length for curtailment. You can see here that higher steel is displayed up to half the distance. That's because I have manually overridden the 3 of 12 to 0.5. I will remove this 0.5 and see what happens. After removing 0.5, the graphs are updated to program recommended value, which is 0.23. If I provide less steel, let's say if I remove 3 of 12 from left support, the graph turns red to highlight the deficit steel. Now coming to the drawing part, the detailing style can be personalized. The distances can be rounded to given multiples. All distances are rounded towards conservative side. Different elements of drawings like beam outline, rebar, dimensions, etc. are drawn in different layers. The layers are set over here. It becomes easy to manage the drawing at later stage. The dimension style, the text style, and the leader style can be set over here. I will begin by attaching a ETABS model. Here is a very simple ETABS model. It has 4 stories, 1, 2, and 3 are typical. Now the model is attached, I will import stories and the load combinations. I will select stories 1, 2, and 3 and all factored load combinations. The sections and forces are being imported. While importing forces, the program checks if same section is assigned for a given beam at multiple levels. If not, such beams are brought to the notice of user. There are 2 more methods of importing forces. In the second method, the user has to dump the forces and the program will import sections for the beams available in the forces. Again, the section assigned is checked. In the third method, the user has to paste the property definitions, the frame section assignments, and the forces. Right, now all the forces are imported. Now envelope of forces is being generated. Here, the user may join any split beams. A beam may be split for various reasons. For example, if a beam has varying section, that beam may be split in parts and assigned different sections. Such beams may be joined over here. Since there are no such beams here, I will copy the beams from summary and I will connect the beams. Okay, here I will set up basic design data. The concrete strength and the rebar strength, the covers, and the limits for color formatting. In this table, I have to input the ETABS beam IDs and supporting data for design. Suppose I have to design grid A and grid B. The respective beam IDs in ETABS are B25 to B27 for grid A and B28 to B30 for grid B. The beam dimensions are updated by the program itself, so I will remove this. Other data I have to input is end conditions, ductile design option, end length offset option, support width and level of beam. Different end conditions are simply supported, fixed, cantilever left fixed, cantilever right fixed, and same for prop cantilever. Now I will update the dimensions. Now I will change the level of second span of grid B, beam 2 plus 200. I will copy forces and draw graphs. I had designed these beams already earlier. Now I will draw beams in AutoCAD. Drawing is complete and adequate details are present here. Only a little formatting may be required, like adding grids or showing bend lengths. Change in level is taken care here. So that's it. If you like my work, do like the video. Thank you for watching.